everyone. My name is Kayo Yen, and today I will talk about my work interpreting language models with contrastive explanations. And this work was done in collaboration with Graham Newbig while I was at CMU. Okay, so the aim of this work is to explain why a language model predicted a certain token given a certain input. And although there's many works in NLP interpretability, surprisingly, very few works so far have attempted to explain why a language model predicts something. And this is because when we apply existing feature attribution methods to language model predictions to measure which input tokens have the most influence on the model prediction, we find that they almost always select the input token that immediately precedes the prediction token. And it does make sense that this is the most influential token, but it's also not very informative. The previous token could explain some features of the prediction, such as that it is likely a verb and a verb that ends with ing, but this does not explain often more important or more interesting distinctions, such as whether it's an action verb that is related to a dog or whether it's a positive or negative verb. And the output space for language modeling is also very large, and it's usually orders of magnitude larger than text classification, for example, which is a task where input saliency methods have been used in the past. So in this work, we propose to address the complexity of language modeling, and we design a more intuitive interpretability method using contrastive explanations. Contrastive explanations try to explain why we have an outcome A instead of an outcome B. And research in cognitive science have shown that this is also how humans tend to interpret things. So when we ask why something happened, implicitly, we're always trying to compare that to another outcome. So now if we use contrastive explanations, we find out that the word dog has the highest influence on why the model predicts barking instead of crying, which is a verb that is less often associated with dogs. And if we change the foil for the explanation, the contrastive explanation can also change. And to explain why the model predicts barking instead of walking, which is also a dog behavior, but has less of a negative connotation, then the word stop becomes the most important word. So now I will talk about how we designed contrastive explanations for language models. And to do so, we extended three existing feature attribution methods to the contrastive setting. So here we have the definition for the original input times gradient attribution method, where we first calculate the gradient according to the input, where YT is the target token, X is the input sentence, and then Q of YT given X is the prediction of the model for the probability of the target Y. And then once we have the gradient, we simply take the dot product with the input embedding of the input token that we want to calculate the saliency for, and we get the importance score for how much that influences the model prediction. And using this method, this is something that we might obtain where the tokens in red are the most important for the model prediction, and the tokens in blue negatively influence the model prediction. And we extend this to the contrastive setting by defining the contrastive gradient, which is the gradient of the difference between the model output for the token YT minus the model output for the FOIL token YF. And we simply replace this in the formula for contrastive input times gradient. And using this, we can obtain something like this, which essentially tells us how much a certain input token can make the target more likely, while at the same time makes the FOIL token less likely. And in our work, we experimented with three saliency methods, which we extended to the contrastive setting. So we have the contrastive input times gradient, the contrastive gradient norm, and the contrastive erasure. And you can find more details for these methods in our paper. So now I will show you all some of the results from our experiments that are aimed at exploring how contrastive explanations are superior to non-contrastive explanations. And first, we found out that contrastive explanations can better identify expedience that we believe a priori should be important according to a certain linguistic distinction. So to verify this, we used a data set called BLIMP, which consists of minimal pairs of English sentences that contrast in grammatical acceptability, with examples in a variety of grammatical phenomena. So for example, in the first sentence, it is grammatically correct. And the second sentence differs only in one word, but it violates the anaphor number agreement rule. And then we created a set of heuristic rules to identify which words enforce the grammatical rule in each of these minimal examples. And we mostly use tools like Spacy and other NLP libraries to perform parsing and other linguistic analysis. So as an example, for pairs that contrast in anaphor agreement, we would extract the co-referent words in the input that is co-referent to the target. So in this example, we would extract teenagers because that is what enforces the grammatical acceptability rule. And I will skip through these other examples for the interest of time, but you can find more details in the paper. Okay, so using these linguistic rules, as well as the contrastive model explanations, we can obtain vectors that encode the two types of evidence. So on the left, we have a binary vector, which encodes the linguistic rules, where we have 1 if the token has been selected by our rule. And on the right, we have an example of an explanation vector where we have the saliency score for each word on the importance of its contribution to the model prediction. And we can obtain the alignment between these two by, say, computing the dot product between these two vectors. In our paper, we also explore other alignment metrics such as probes needed and mean reciprocal rank. And overall, we find that non-contrastive explanations don't do much better in terms of alignment over a random baseline. And then contrastive explanations have better alignment than their non-contrastive counterparts, which are in blue. And we find that this is even more so the case when the model predicts the correct word. And we also find a positive correlation between the difference in alignment scores between the contrastive and the non-contrastive explanation against the distance of the target to the selected evidence that enforces grammatical acceptability. So this shows that contrastive explanations outperform non-contrastive ones even more when the known evidence is distant to the target. So our second finding is that contrastive explanations can better help human users predict what the model would have predicted. So to do this, we performed a user study where we created a web interface shown here. And for each task, we ask, so we show a explanation for the model prediction from GPT-2 model. And then we ask users which token they think that the model selected. And we also ask users whether the provided explanation was useful to them for their answer. And after each turn, we also give feedback whether the user predicted the model correctly or not. This way they can also kind of learn to use the explanations during the test. And we conducted a study with 10 graduate students in machine learning with 20 pairs of highly confusable words, which we defined using a corpus-driven metric to measure confusion. And we also balanced the data so that we have an equal amount of the correct answers. So in this case, either herself or himself, and then an equal amount of whether the model performs a correct prediction or not. And our study shows that users are more accurate in simulating model behavior when they are given some explanation compared to no explanation at all. But it also shows that for each explanation method, the users are more accurate when they are given the contrastive explanation compared to the non-contrastive one. And the difference here is also statistically significant. And we also find that contrastive explanations are statistically significantly more useful as self-reported by the users in our study. So overall, contrastive explanations improve model simulatability, which is one important facet of evaluating interpretability methods. And now our final experiment demonstrates that we can use contrastive explanations to also characterize how language models make certain types of linguistic distinctions. So we hypothesized that given different target FOIL pairs, the pairs that represent linguistically similar decisions will lead to similar types of contrastive explanations. So in other words, we believe that the model uses similar kinds of signals from the input to perform similar kinds of linguistic distinctions. And so to explore this hypothesis, we clustered different FOILs according to the contrastive explanation that's associated. So to do so, given an input sentence and a target, we first compute the contrastive explanation for each possible FOIL. So we get an explanation for, let's say, white black instead of red, and white black instead of Asian, etc. And then we performed k-means clustering over these explanation vectors that we obtain, so that we obtain clusters of FOILs that are similar in associated contrastive explanations. And then this step allows us to find certain clusters that may relate to a type of distinction. So the example here shows that the model uses similar kinds of input evidence to choose black instead of another word that describes the color. And finally, by looking at the mean of the explanation vectors for a given cluster, we can also see which input words exactly are important to make this kind of distinction. So in this example, the word relativity makes the word black more likely than any other color. And our goal is to perform an aggregate analysis across several examples. So we scale up this cluster analysis that was previously described to a lot of examples that took a lot of time to compute. And then we also wanted to verify how valid this clustering method is. So we show that this is indeed valid by verifying that we can find clusters that are associated with a priori known linguistic distinctions. So in this example, to recover and for agreement, we found that if the target is he, then we can find that like all the feminine pronouns are clustered together. And I will skip through the other examples in the interest of time. And then we performed an aggregate analysis, which I think was really interesting. But I will leave you all to check out the paper to find out what we learned about how GPT-2 makes predictions. Okay, this is super interesting, and I really like this, but I don't have time. So but yeah, so we also applied this to NMT as well, and it works. It seems to work as well qualitatively, and we include this in our demo as well, so you can play around with language models and NMT models. And yeah, so I want to summarize the three main findings of our experiment, that contrastive explanations seem to be more useful to explain language models than non-contrastive explanations. And you can use the QR codes here to check out the paper, as well as the code that has the interactive demos on Colab as well. Thank you for your attention.
Thank you, Kayo. Quick questions. We have time for maybe one or two very quick questions. There is one all the way in the back. While somebody's getting there, maybe I'll ask a quick question. So thinking about integrated gradients, which is another of these interpretability things, it has a reference sort of instance and the instance that you're comparing against. And instead of taking the difference of the gradients, they take difference of every point in between the interpolation. And there's sort of theoretical reason why that might be better. Do you think that also applies to this contrastive stuff?
Yeah, so I definitely think that so like we only had time to explore three instance attribution methods in our paper, but I do think that if we extend, for instance, the integrated gradients to the contrastive setting as well, then I think the argument that people tend to interpret things contrastively, and this can also entangle all of the different types of decisions that come into language modeling, would also help for integrated gradients as well, even though we do do the integration part.
Okay, cool. I guess the mic's there.
Hey, thank you for the great presentation. I just have a quick question about the method itself. So do we have to specify the comparing word beforehand, or are you taking expectation over all the words in the vocabulary?
Yeah, so you do have to specify the FOIL beforehand to compute the contrastive explanation. And I think choosing what FOIL is the most meaningful for an explanation is also an interesting research question in itself. So in our study, depending on the experiments, we either chose the FOIL as something that denotes a linguistic distinction. So that's different in terms of the number or the gender, etc. And then we also chose foils depending on the confusion score. So like depending in the corpus, like how often are the two tokens sort of like interchangeable or appear in similar kinds of contexts. But yeah, I think like there can also be like more work into looking into like what are kind of the contrastive explanations that are the most useful or the most illustrative for people to see, and then choose the foils accordingly.
So just a further question on this. So
Mhm.
did you find any cases where your explanation changes if you were to change the foil word that you're
Yeah,
talking
so
about?
my first running examples showed that we had barking as the target, but then if we contrasted barking to crying, then the word dog was the most important because crying is not really a dog kind of verb. Whereas if we change the foil, but then kept the input and the target the same, but if we change the foil to walking, then walking is also like something that dogs do a lot, but it's not something that you want to stop dogs to do. So stop was the most salient word.
Okay, thank you.
Thank you.
Let's thank Kayo again.